Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, minimum speed to arrive on time. So here we have a floating point number hour that we get in the input. And this represents the amount of time you have to reach the office. So you are going from one point to the office. So for example, here it takes at hour 6, you arrive at the office. And to do that, you must take n trains in sequential order. So what this means here is that you take train 1, you take train from 0 to this place here, takes you 1 hour, and then you go here, it takes you 3 hours, and then here it takes you 2 hours. Sorry, not 2 hours, but 3 kilometers and then 2 kilometers. So to get here, it takes you 1 kilometer. Yeah, it takes you 1 kilometer, and then here it takes you 3, here it takes you 2. Okay, so this is the distance in kilometers of each train ride. And then each train can depart only at an integer hour. So what this means is that if you arrive, let's say at 1.5 hour to the first train, then you can depart from the second train only at hour 2. Okay, because you have to depart at an integer value. So that's one other constraint we have here. And the goal is to return the minimum positive integer speed, which is basically how many kilometers per hour each train can take, so that all the trains, so that you can travel all the distances here and arrive at the office on time. And by on time means before or equal to this hour. Okay, so that's basically it. So let's summarize it again. So you are going from one point to the office, and you have the distances of the trains you need to travel through in kilometers, of course, and you need to find the minimum speed you need to have to be able to arrive at the office. And if it's not possible, we want to return -1. So let's take this first example here. So the first example, we can actually just take speed 1, because then we'll arrive at for the first train, 1 kilometer. That would be with 1 kilometer per hour. It will take you 1 hour. To take the second train, for the second train, 3 hours. So at speed of 1 kilometer per hour, that's 3. So now you have 4. And then plus 2, now you have 6. Okay, so you'll arrive exactly at 6-hour mark, and so that means this is can just return speed 1 because it works. Now for the second example is more interesting. So for the second example, the best we can do to arrive, the minimum speed is actually 3, because you take for the first train 1 kilometer with speed of 3, you will arrive at 0.3 hours. But since you have to take a positive of an integer value to depart for the second train, you have to depart at hour 1. Okay, so if you depart at hour 1, that means here this is 1. For the second train, 3 kilometers with 3 kilometers per hour, that's 1 hour. So now 2 hours. And then for the last one, 2 divided by 3 is this. And so now it's 2.66 all the way 7-hour mark, which is smaller than 2.7, so we are good. Okay, now notice here for the last train distance, we didn't take the full hour. This is because for the last train, we don't need to depart again, so we don't need to get to the full hour. We arrive at this moment, and that's enough. Okay, so that's one key insight here. Yeah, so if we look at the constraint here, the number of trains is 10 to the power 5. The hour itself is 10 to the power of 9. So this tells you that we definitely can do any O(n) squared solution, or any thing that goes through n and then goes through hour or goes through distance. And so how can we do better? The way this question is framed actually really gives hints to binary search, because we have a large space of speeds that we need to choose the minimum from. And then we have a constraint, and you should immediately think of binary search with things like this. So let's see how we can tackle it. Okay, so with binary search, like usual, what we need to find is a monotonic function that is either first the values are false, and then once they become true, they stay true, or this other variant where once they become false, they stay false. Okay, so and this would be the function that we will evaluate for our binary search. So let's see if we have a function like this. And so since what we are looking for is basically the minimum positive speed, integer speed, which is basically kilometer per hour, that we can use to arrive at basically before or equal to hour. This is what we're looking for. And so usually this x value should be whatever value you are looking for. So here we are looking for the speed. So let's say then f of x, let's just have it as the minimum. Okay, so basically it's whether we are able to arrive at this speed. Okay, so this basically tells us, is it possible? So it's a Boolean value to arrive at office before or equal to hour with x speed. Okay, so x here is x kilometer per hour. Okay, and if we take a look at this, then one observation we can make is that if you can arrive at 3 kilometer per hour speed, then if you increase your speed, let's say to 4 kilometer per hour, you will still arrive. So let's say I'm able to arrive with 3 kilometer per hour, I'm able to arrive at the office at hour before or equal to hour 7. Then if I increase the speed, then it's logical that I will be able to arrive before 7, even before the time I arrived with 3 kilometers per hour. If I take 5, I should be able to kilometer per hour, I should be able to arrive. And so once we are able to arrive at a certain speed, if we increase the speed, we'll be able to arrive either at the same time or even faster. Okay, so that means this is the monotonic function we have, because we are not able to arrive, let's say, at 2 kilometer per hour and 1 kilometer per hour. So first the values were false. And then once they reach 3 and they are true, as we increase the speed, the values stay true. Okay, and so this is the one we are going to use. Now we can apply binary search with this. The only remaining thing to think about is how do we compute this function f of x, and what are the bounds for our low and high. And then we can use our template binary search. Now for f of x, well, we just want to know if we are able to arrive, so we can just go through the distances. Okay, range of, so n, let's have n be the length of the distance. So one thing to note here, like we saw in the second example, is for the last train distance, so we had, let's say, 1, 3, 2. For this one, if we take, let's say, speed 3 kilometers per hour, 2 divided by 3 gives you 0.667. We don't need to round this to 1 because we don't have another train to go to. But let's say for this one, at value 1 divided by 3 is 0.33 something. Then we have to round this to 1 because we have to depart from this train at a full integer. Okay, and so that means for the last distance we don't need to take the ceiling, because to round here to round up, we need to take the ceiling of the value here. And so for the last train we don't need to do it, but for the ones before we need to do math.ceil. So that means here we can just take everything before the last one and have arrive, which tell us when do we arrive at the office. And then here we just add the distance divided by the speed, which is x, to know when do we arrive. That's what we did here, that's what we did here. And then at the end we need to add the time it will take to arrive for the last train. And here, as I said, here we need to take the math ceil in Python, but for the last one we don't need to. So dist of I divided by x, and here we can just take dist of the last value divided by x without the ceiling. And then how do we know if we are able to arrive at the office? Well, we just check that the arrive time is smaller or equal to hour. If it is, then this means we are able to arrive at the office with X speed. So this is the function we use for our binary search. Now the last thing to think about is what is our low and high value. Well, with this method of binary search of a monotonic function like this, we just need to find boundaries that maintain, okay, that that are either outside of the bounds or maintain that these constraints are valid. So the problem here is that we can have a case where it's all false or a case where it's all true. Okay, and so we take low and high outside of the bounds, right? So that we prevent, for a case like this, we prevent not finding a solution, or for a case like this, we prevent not finding a solution because high needs to be outside of the bounds. So what are the values outside of the bounds? Well, we know for a speed of 0 hour, you won't arrive anywhere, right? So that's outside of the bounds, so let's just take it. So low, I'll set it to 0. For high, let's just take the maximum possible, which is 10 to the power of 9. You can also do 10 to the power of 9 plus 1, because the problem's constraint tell us that the highest value for hour is 10 to the power of 9. Okay? And so if we take this low and high, we should be able to solve it. Okay, so that's pretty much it. We have the structure. We know our f of x. We just write template binary search. Now, in terms of time complexity, this is going to be O of flag n, and n being the search space, and the search space is the speed, and so the speed can be at most hour, and so or the number of trains. So this should be good because both hour is 10 to the power of 9 and n is 10 to the power of 5. Okay. And then our f of x function actually is O of n. And so for our binary search, so let's say this is O of h, and this is n, so it's going to be O of n log h. So that's pretty much it here. Now let's solve this and code it up. Okay, so let's code up the solution we just saw in the overview. So we need our function f of x, and then we need to do the structure for binary search. We said that we will take n, and then while let's actually just take here and plus 1, while high minus low is bigger than 1, because we want at the end, we want to have when we have something like this, we want at the end, we want to exit when low is here and high is here. Okay, so when high is right here and low is here, so the difference is 1 between the two. And so we take mid for binary search, and then to avoid overflow, let's just divide it with binary, and using binary method, and then we check if f of mid is true. Remember, the invariant is that high needs to always be true. So we set high to mid then. And then if it's false, we want the invariant is false. Low needs to always be false, and so we set low to mid. And our solution should be high, but sometimes it's not possible. So if it's not possible, then high will not be true. So if all of these values were false, then high would be false, but it can be true, right? And so we want to check here if f of high is true, then that means that we have a solution. So otherwise we don't have a solution, so we return -1. And now we can just write our f of x. So we said the arrive time is arrive, and then we return if this is before or equal to hour that we need to arrive at the office. And then now here we just go through the range. So we need to say distance, and here we do n-1 because for the last distance we need to add it without math seal. And so for the last distance, n-1 divided by x, we just add it without rounding up. But for the ones before, we want to round up, so we do arrive plus distance of I divided by x, but we round up with math.seal. Okay. and this should work. So if we just run this, looks good. Let's submit. And this passes. Okay. Yeah, so that's pretty much it for this problem. A very straightforward implementation of binary search, but you need to really be able to write binary search on functions instead of just on arrays. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you on the next one. Bye.